All right, so welcome to lecture one. I'm going to try to record the lectures. That's why you see me with a Windows tablet. This software that records the screen also compresses it on the fly, which is amazing for a tablet that is not very powerful. I can get video files that I can upload directly. I should introduce myself first, right? Unfortunately, I don't have a web page, nothing more than a LinkedIn page, which is what I typically show people who want to know more about me. All right, so this is me. I think. All right, this is me. So I'm Razvan Vojko. Please call me Razvan. Skip the prof. All right, really not needed. I just started to work with Indeed.com last Friday. Before that, I used to work in Facebook, and a very long time ago, I used to work in NUS as a senior lecturer, and I still have an adjunct position with the department there. I enjoy teaching very much, which is why I come back and do a little bit of this every once in a while. And I teach quite a few classes. So the other half of the semester I taught C, and I have a class on programming language implementation in NUS in the second semester. But together we're going to try to explore Python, which is an introductory course in programming, essentially. Yes?
Is this not the C class?
No.
Oh.
So there's two Python classes, there's two C classes. All right, so the other C class is taught by Bruno, I think. And it's not on Mondays. I think it's on Tuesdays and Wednesdays, or Tuesdays and Fridays. It's still here. I think it's still here.
In the first half of the sem, I think it was Monday.
Yeah, in the first.
Blessings is here 18. Bye, I'm out. Nice to meet you. Professor
No worries.
Razvan, yeah. I'm not in this class.
No worries. Good luck with C.
Thank you.
You're gonna need a lot more luck there. Cool. So together we're gonna try to explore Python. Python is a language that was designed to be a learning language, and it started in 1994. Many people have the impression or the feeling that it's a new language, it's a newcomer on the block. Actually, it's not. It's older than Java, right? So Java will be soon. 1995. Yeah, it's coming to close to 25, and I think so. Next year, Python will be 25 years old. And it has evolved quite a bit, and we're going to talk a little bit about that. But it was designed to be a learning language, right? It's designed to be very, very simple. It abstracts away. We use and you're going to hear this word abstract quite a lot. It hides, right? It hides a lot of the complexity of computers, and it's trying to expose the mathematical nature of programming, of algorithms. Right, without forcing you to think about bits and the way the data is organized in memory, and the fragmented nature of memory, and so on. In that sense, hopefully we're going to be able to focus on a few aspects of computational thinking rather than computing, right? And algorithms. All right, we're going to try to push our applications toward data science, data processing. We're not really going to do data science, but I think for many of you, programming as a concept is new, right? This is the first encounter with programming at all, right? So you don't have any notion of algorithms. So we're going to try to look a little bit at algorithms. All right, so the most used and also the oldest implementation of Python is the one that you find at python.org. This is the website. And if you haven't done that already, I would like you to download it and do it now. So you have a link to download here, and you have Python 3.7.0. You can get either the 64-bit version or the 32-bit version, right? So using the 32-bit is a bit wasteful, but you won't notice a difference. So if you by mistake have already downloaded the 32-bit version, don't worry about it. The website has changed a little bit since I last saw it. So where do we download it from? Binaries for also work on processor, blah blah, embedded, and can I just files? All right. So you want the executable installer if you're on Windows, right? How many of you are on Windows? 2, 3. Okay, good. So yeah, I mean, normally I would say PTU, but today I'm using Windows. Normally I use a Mac. It's in the bag, and I very much prefer Macs for everyday work. But if you're on Windows, you have to get this one, right? If by any chance you get this one, right, that's fine for this course, right? But just that if you're doing more work on Python, it's a bit wasteful to use the 32-bit version. If you're on Mac OS, you again want the 64-bit version. All right. If you're wondering what's the difference, the difference is that the 64-bit version is a bit larger, takes a little bit more space on your disk, but allows you to access more data at once. So if you do processing, if you have a machine that has 8 gigs, which probably most of you have, at least 8 gigs, you cannot, so with 32-bit versions of any kind of software, you cannot access more than 4 gig of data at once. So you essentially cannot take full advantage of your 8 gigs of memory, because whatever program you write in a 32-bit compiler or interpreter is going to access only 4 gigs. All right, and this tablet, as puny as you see it, already has 8 gigs, so I'm using the 64-bit version as well. So if you haven't done that already, you should try to install right now. If you're on a Mac, you already have a Python, but typically you would have a Python 2 version of the interpreter. I very strongly recommend to use Python 3, so actually to install a new version. There are significant differences between Python 2 and Python 3. There's a long story of how Python 2 is still in use, right? It's the plan of migrating from Python 2 to Python 3 is 12 years old. About 12 years ago, they decided that Python 2 had some major flaws, and they corrected them in Python 3. So Python 3 is not backward compatible. Python 3 cannot run all the Python 2 programs, right? And they created a migration plan, and then they kept both versions alive, trying to backport all the new features of Python 3 back into Python 2, so as to support the existing programs that were already written in Python 2, right? So those users will not feel unsupported. The pressure was so high that 12 years later, they have not managed to cut off Python 2, right? So Python 2 went from, I think, version 2.1, which was supposed to be the last one, up to version 2.7, right? Which is in parallel with Python 3, which is now at version 3.7. So version 3.7 should be in sync, more or less, with version 2.7. But there are syntactic differences between the two versions of the language. that will make Python 3 programs not run in Python 2, and therefore you're going to encounter trouble. So I recommend that you upgrade to Python 3. Last year somebody came and said, oh, but Python 3 is weird because they learned in a different class and then about Python, and then that teacher was not updated enough, right? So that teacher didn't want to upgrade himself to Python 3. So for like 11 years, he had 11 years to perform the conversion. He didn't do it, right? And then his explanation of why not using Python 3 to his own students was, but Python 3 is weird. It's not. Python 3 is the future, and everybody, or a large size of the community, is hoping that Python 2 at some point will be done with and forgotten and never seen again. Myself included, and therefore the class will be exclusively on Python 3. I will not talk about Python 2 at all. If you want to use the code in Python 2, you're doing it at your own risk. Cool? So everybody has Python on their machines, because I see that nobody is scrambling to install anything. Yes? Cool. So there are multiple ways of running Python. The easiest way, which is possible in Windows and Mac, not on Linux. Anybody on Linux? No. All right. I am very frequently on Linux. Is the font large enough? Let's see if we can actually increase the font a little bit. So the easiest way is to start this shell called idle. So if I go here and somewhere under Python, I should have a folder. Yeah, here I have a folder, and here there's this idle, all right, which runs this environment. And I was promising that I might, if I just say Control-Shift+, that doesn't help. Options. Okay. So let's see if we go to 16. Okay, this is better. And what you see here is essentially an interactive console. And if you're a learner, it's probably the easiest way to interact with Python. Alternatively, you can go to the command prompt. Is everybody familiar with the command prompt? Has each of you seen this before? So you can get it by saying Command R and then CMD. This will run another window of the command prompt. And in here you can run command line code, like for instance dir, which will tell you the contents of the directory, right? A much more typical way of interacting with a programming language is from the command line prompt. And for Windows, it's Python is not so nicely positioned, right? So you have to run it through this very long line. But if you're in Linux or on Mac, you can just say Python or Python 3, right? Then you're going to run the interpreter. And then everything we do from here, we can, 2 plus 3 will be 5. Exactly the same interaction happens here, right? So I'm going to use for a while this interactive environment. First of all, it's white and projects more light, so the room doesn't appear so dark. But also you won't see a significant difference. But at some point we're going to move into creating Python files and running those files from the command line, right? So we're going to experience that as well. Be prepared for that to happen. Okay? Cool. So let's learn the very basics. How is this course gonna be structured? We're gonna type together as a lab, right, and see code running together, right? All the files that we create in class, I'm gonna make them available to you. We're going to record the screen, and the video recordings are gonna be available to you as well. There's gonna be 5 assignments of increasing weightage. So we start at let me see, we start at 10, I think, and we end at 25. So it's going to be 10, 15, 20, or at 30, or at 5. So 5, 10 is 15, plus 15, 30. 30 plus 20 is, I think we start at 10. So 10, 15, 20, that's 45. And it has to add to 100, right? So, so 2 plus 3 plus 4 plus 5, 5 plus 6. We can use Python to perform the computation. This is 20. Okay, so we start at 10, right? So 10 plus 15 plus 20 plus 25 plus 30 is 100, right? So first assignment is going to be 10%, next one 15, and so on, right? With the last one having the highest weightage. So you're going to warm up through the course. They're going to also become more difficult, but as you're warmed up, it should be fine. All right. Elements of the language, right? You're seeing already that we can evaluate expressions. Any kind of arithmetic expressions can be evaluated, and Python is very nice. Everything has a value, right? Not all languages are like that. So you sometimes have statements, the statement execute, but they don't necessarily have a value. In Python, everything has a value, right? And interestingly enough, when something doesn't have a value, we invent a value called none. And that's the value of the statement that has no value, right? So in the end, everything has a value. The alternative way of putting 100 on the screen is to say print 100, right? So this is a statement that doesn't have a value, but puts 100 on the screen. And you're going to say now that, well, I'm not seeing any difference, all right? So let's see where the difference comes in. One interesting thing that can be done in programming language is to store a value somewhere. And these storage places, we call them variables. All right? This is a symbolic name that is assigned to a piece of memory. We don't know where that piece of memory is. We don't care, because whenever we want to refer to it, we just say X, right? So we can store some stuff there, and then we can retrieve it later. So I can say X is 100, for instance, right? So notice now that this statement doesn't have a value, right? And when I say the value of, I want to retrieve the value of X, I can say 100. I can also say now X equals print . The keyboard is a bit wonky, and I'm not in a good position. I would prefer the desk to be a lot lower. So notice what happens now, right? The 100 does get printed. So previously it didn't get printed, right? But now when I say X, I want to get the value, there's nothing really there, all right? And that's because actually whenever a value is none, actually, depending on the configuration, Python avoids printing it, right? But I can say actually X equals none, and that will be true, right? We're going to get what this equal means later, but essentially I want to test what X is none, and I get true. And notice that I can reuse X, right? So initially I have put 100 inside X, and whenever I want to evaluate X, I get whatever is inside there. Then I want to put the result of print 100 into X, right? And then I can use whatever is there. So there's two aspects related to a statement, and what we have done here, we have created a statement, a Python statement, right? This is one, and this is another one, and this is another one, right? There's a value and there's a side effect, right? So in this case, since we have a print inside here, the side effect of print is putting 100 on the screen, all right? And the statement itself doesn't have a value. Whereas here, this statement has no side effect, all right? But 100 has a value, all right? And we're going to have to keep that in mind all the time, all right? We're going to start dealing with side effects a little bit later. But if you look at Python code, you're going to see print being used very frequently. And then when we're going to go to using files, you're going to see that even though the values exist, we cannot see them anymore, right? Only inside this environment do we see the values, okay? So then we're going to have to resort to print in order to see any kind of output from the program. Okay, so one thing we have learned is expressions, all right? And another thing that we have learned is assignment. The equal sign means that we're changing the value of x, all right, to have a new value. Okay, and we can reuse that. I can later say x is assigned 200. All right, and then the value of x becomes 200, right? I can also say print x, and I'm going to get 200, right? Again, this is actually the value of x, and this is a side effect that prints the value of x, and the value of print x is none. Okay, cool. And in this way, we have introduced numbers, right? So numbers are one form of literals. Literals are parts of the language that stand for what they are, all right? And we have several such kinds. One is integers, right? And this is what we're seeing. Another one is strings, all right? So we're going to say this is a string. All right, and then as we print x, as we get the value of x, we see that this is a string. And notice the fact that I can reuse x. I can reuse x with a string or with a number as I please, right? This is also something that is not typical of most languages. All right, this is not necessarily something that people like in Python. Notice that we have used double quotes to define the string. When the string is printed, it has single quotes. All right, and if I do print x, you're going to see no quotes, right? So let me explain the single quotes. Double quotes or single quotes are fine, doesn't matter, right? If you start with double quotes, you have to end with double quote. If you start with single quote, you have to end with single quote. Why is that? Well, for instance, you have a string where you want to use double quotes inside. How do you do that, right? So I'm going to say y. And I'm going to say this is a string with all right, so because I have started with single quotes, these double quotes appear as regular characters. They don't end the string. The string ends only when we encounter the matching single quote, right? And we can see y now, and y gets printed in single quotes. But what if we want to use single quotes inside? Then we're going to start with double quotes. Right, and if I print z, notice now that Python has figured out that there are single quotes inside, so better use double quotes. When we use print, notice that the enclosing quotes are missing. And again, the enclosing quotes are missing. Why do you think they're missing?
Because the quotes are containers, so to show up.
Yes, so why do they appear when I evaluate and they don't appear when we print?
Because if you say z is equal to this tree, then z is referring to this tree. So when you print z, it will give you the string itself.
Not really. So having this evaluation, right? I type z and I get the value of z. This is a learning feature. Most of the time, you don't want to use that. You're not. We're only going to use this for in the beginning, right? And if you're going to become experienced Python programmers, right, you're not going to touch this idle environment ever again, right? After some time, you're not going to do it, right? So this is sort of debugging feature. It's a learning feature, right? You're evaluating y, and the interpreter doesn't only tell you the value; it also tells you the type. So by giving the quotes, it reminds you that it's a string, right? However, in regular use, when you use Python from Python files, from source files, which is what we're going to do very soon, we're going to just resort to print. And when you print, you just want to print stuff. You don't want to print it quoted, right? If I want to print hello, and it would be good if I could right? I don't want to print it quoted, right? I just want to print hello. Imagine that whenever I use print, all the time I have quotes. Then I could never print whatever I want. Everything would be quoted, right? So that doesn't make sense. However, when I evaluate stuff, yes, I want to know the type. That's a learning feature. I am in this environment because I want to learn. Every once in a while, I'm going to do stuff, and then I want to see what have I done. Let me evaluate this variable, that variable, see what values they are. Am I happy with those values, right? And then you want to know the type at that point, right? But that's not something you would do in production code, in real life code. So we have numbers, we have strings, we have actually two types of numbers, right? We have integers and we have floating point numbers. So if I'm going to divide 2 by 5, I'm going to get a fractional number, 0.4, let's say. Okay? And this is essentially a different kind of number. It's encoded differently, and we're going to explore the differences between the two types of numbers. Okay? So let's see what are the typical operations for numbers. All right? They're all the usual ones, right? So we've seen addition, I think. We've seen, let's see multiplication. 2 times 3 is 6. All right. Let's see. We've seen division, right? But 2 divided by 3 gives us a fractional number, right? Well, the interesting thing is that we can also do integer division, what we call integer division. And I'm going to say 12. And I'm going to use a double slash 5. And you see, 12 divided by 5 would be 2 point something. But we want the integer part of that. All right. Then how about the remainder, right? Because if I divided 12 by 5 and I get 2, I also like to know the remainder of that division, right? So that can be obtained with the operator called percent. 12% 5 gives me the remainder. All right, let's do a 13 maybe. So 13 divided by 5 is 2, not 3, 13 is 2. 13% 5 is 3, right? So that's the remainder. So typically what we want is that 2 times 5 plus 3 should be the original number. The interesting thing is what happens when we deal with negative numbers, right? So minus 13, integer division 5. All right. And this is where Python got things correctly. The correct result is minus 3. Right? Cool. Most languages will give you minus 2. All right, so Python arithmetically correct. Minus 13% 5 is 2, right? The remainder is always positive. If you do this in C, you're going to get minus 3. So the quotient is minus 2 in C, and the remainder is minus 3. Totally wrong, right? Why? Because actually the underlying Intel arithmetic unit in the processor is wrong. And Python, by definition, will not implement its own arithmetic operations, but would rather rely on whatever the processor is providing, right? So if the processor provides the correct operations, then in C you would have the correct operations. Python nevertheless goes to the length of defining its own operations in such a way that they are mathematically consistent, all right? So remember, what we want here is that minus 3 times 5 plus 2, we want this to be the original number, which is minus 13, right? And this is the remainder, and it should always be positive, right? Cool. And surprise, surprise, we have the power operator. So let's say 4 to the power of 3 will yield 64, which is 4 to the power of 3, right? So the double star is the power operator. This is, again, an operator that doesn't typically appear in many languages. They will have some function, and we're going to see what functions are, but it's not a primitive of the language. In Python, it is. All right, another very interesting thing that we have in Python is complex numbers. Everybody knows what complex numbers are? Yes, no, maybe? Yes? Not everybody is fully convinced. Do you know what complex numbers are? Okay, cool. So why do you think so and you don't know? Why aren't you sure?
And then I can't remember whether I got it right.
So what's the square root of minus 1?
I.
I, right? So we don't know what it is, so we invent this symbol, which we'll call I, which is the square root of -1, right? And then, based on that, assuming that the square root of -1 is an entity that we can deal with, right, we figured that actually a complex number is made of a real part and an imaginary part, right? So you can write a number as 2 plus 3 times I, small I. And you may want to multiply this by 3 plus 2 times I, right? And really? Oh, okay. There's no multiplication, sorry. 3I, that's how we write it. Oops. Let's find out. All right, so if I say complex of 2 and 3, what do I get? Oh, J. You know why it's J and not I? Yes, no? Engineers don't like I. I is for I is reserved for intensity of the current, right? So my undergrad studies were in electrical engineering, in computer engineering, right? And I had to go through the switch, right? So after high school, complex numbers were something plus something I, and then I had to switch to something plus something J, and yeah, I haven't used Python complex numbers for a long time in Python. I did teach this course last year, and I did touch on them, and I've probably forgotten ever since. But it's J. All right. So how does the multiplication happen here, right? So we're going to have 2 times 3 as the real part, which is 6. But we're going to derive another real part from 3j times 2j, right? And that's going to be -6. So 6 plus -6 is they're going to cancel each other. So we're going to be left only with the imaginary part, which is 4j plus 9j, which is 13j. So we can very easily work with complex numbers. Now, interestingly, you can apply the sine function and the exponential function to a complex number, right? There's actually no restriction there, right? And one of the nicest formulas in mathematics is this one, that you have that exp. So actually we do have let's see, e to the power of I pi plus 1 equals 0, right? So you can raise e to an imaginary power. And this is an identity, one of the most striking, because it relates numbers that have very disparate definitions, right? E and pi, they don't seem to have anything together, but yet, right, they do. So we could actually verify that, right? We could use cmath.exp, and I'm wondering whether I should need to import cmath. We're going to talk about imports. So cmath, is this in? Okay, we're going to talk about imports. Just bear with me right now. So cmath dot exp of 3.14159. There's pi is defined somewhere. I1j. And let's see the value of this, right? So you see that we're getting something that's very close to -1, right? Which sort of verifies the identity. But remember that in general, you can work with, you can have the entire arithmetic for complex numbers. Cool. If we stick with the integers, right? There's another important thing that we can do with integers, which is represent them as bits. All right. So let me remember how we can print a number as bits. Print binary into binary. So that could be one way. Okay, cool. So I can say bin, and I can take an integer, right? And what I get back is this string. All right. So bin is a predefined function, and what I get back is this string. All right. And ignore the 0b here. 0b is essentially telling us that this is bits. This is binary, right? What does 1010 mean? No? You're seeing it for the very first time? Completely unfamiliar with this.
It's binary, right?
It's binary. What does binary mean?
It's just like a way to represent numbers with just zeros and ones.
Yes, right? So why is this important?
So it's a language that the computer knows how to understand.
Yes. So what you actually have at the very basic level of memory is bits, right? You have a memory element that that has two states, right? Like a switch. So you designate one of the states as 0 and the other one as 1, right? So you can switch between them, and essentially this is how you store stuff, right? You can if you have if you have something to remember which is one of two things, right? Then you can store it inside a bit, right? You can remind yourself, for instance, your favorite team played yesterday, and it could have won or it could have lost, right? And you want to remember. Maybe it's difficult to remember, right? So you have one switch, and you have one position for win, one position for lost, right? So you put the switch in the corresponding position, and that will remind you, right, whether it won or lost. Maybe you're following very many teams, right? And you have a switch for each team that you're interested in, and then for each team you're going to switch in the correct position, and you're going to know each team whether it won or lost, right? So that's memory. That's essentially a form of storage, and that's what happens at the level of inside the computer. Now we can use a system with two states to count, right? So we can start from 0, as we would start in base 10. Our normal base is 10, right? We do 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and we ran out of digits, so we start using 2 digits. So we're going to say 10 here, right? with base 2, we have only two symbols, 0 and 1. So we're going to do 0, 1, and we have run out of digits. So we're going to go to 1, 0, right? Then 1, 1, then 1, 0, 0. 1, 0, 1, 1, 1, 0, 1, 1, 1. 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, and so on, right? And notice this correspondence here, right? It's 10 and 1, 0, 1, 0, they're on the same line. So we're seeing the same thing, that we have a 10 here and we have 1, 0, 1, 0, right? So essentially, we can keep counting forever, and then we're going to discover that every decimal number has a binary representation, right? And it's relatively simple to find out what it is, right? So if I take 10, I divide it by 2, and I get the remainder of this division, which is 0, right? So this is the 0 that you see here. This is the 0 that you see here. You're left with 5. So if we're very quick, we're going to see that I have 1, 0, 1 here, and I have 1, 0, 1 here, right? So I'm left with 5. But let's continue, right? So remainder is 0, quotient is 5. I divide 5 by 2. The remainder is 1. So you see a 1 here, right? And then the remainder is 2, right? 2 divided by 2, the remainder is 0. All right, which is the 0 here, right? And the quotient is 1. 1 divided by 2, the remainder is 1. And then the quotient is 0, which means that I can stop. So I can produce the digits backwards, right? From the last to the first, by just getting successive reminders, right? The interesting aspect is somewhat different, right? So we can perform logic operations between bitwise logic operations. So if I have 0, 1, 0, 1 and 1, 1, 0, 1, right, I can produce the bitwise conjunction of these two numbers, 1 and 1, right, assuming that 1 is true and 0 is false. 1 and 1, right, should produce true, which is 1. 0 and 0 should produce 0. 1 and 1 should produce 1. 1 and 0 should produce 0, right? So we can produce the bitwise result of two numbers. This is very useful in many cases. And I'm going to introduce these operators. This is where I wanted to get, right? So for instance, I can say 5 and 7. And the result is 5. Not very interesting. Let's take 11. And maybe 10 and 9, right? And that produces 8. Yes?
I didn't fully understand how you represent numbers, because say if you have 2.1, like a decimal number, how would you represent it?
We're only looking at integers. I can explain that, but let's not go there yet. I can explain that. It's much less interesting because you can't have these operators on floating point numbers, on real numbers. Right? So this entire discussion is just for integers. So let's understand how this is happening. So bin of 10 is 1010, right? Bin of 9 is 1001, right? So if you look carefully, right? So this 1 and 0 yields 0, right? 0 and 1 yields 0, 0 and 0 yields 0, and 1 and 1 yields 1, right? And then what I want is the value of 1000, right? So if we check bin of 8, that is 1 0 0 0, right? So just to make it clear again, right? So so this 0, and I should be able to make it bigger. Okay, so 0 and 1 yields 0, right? 1 this is hopeless. Right? So looking at the last digit, right? 0 and 1 is 0, right? Then the 1 but last, 1 and 0 is 0, right? Then the next one, 0 and 0 is 0, and 1 and 1 is 1, right? So this produces the result of 1 0 0 0, which is 8. All right? Does that make sense? Everybody is following? Let's try 10, maybe 9 or 10. All right, so 9 or 10 yields 11. Why? Bin 9 is 1 0 0 1. Bin 10 is 1 0 1 0, and bin 11 is 1 0 1 1, right? So this one or this 0 yields this one, right? This 0 or this one yields this one. All right? Next one is this 0 or this 0 yields this 0, right? And finally, this one or this one yields this one. Clear? Right? So we're going to play with these soon, just to have some application of them. Another one is exclusive OR, right? Which is very interesting. Whenever they're the same, the result is 0. Whenever they're different, the result is 1. Right? So if I'm going to say 10 exclusive OR, which is the caret 9, we're going to get 3. Right? So bin, and I'm going to try to make them sit one under the other. So bin of 10, I'm going to put a \n here. We're going to learn all these things later. Bin of 9. I'm going to put another \n, and we're going to put bin of 3. Yeah, almost. Not quite sure why they don't align, but let's try to force them to align. So I'm going to add one space here. No, I'm going to add one space in this way here. Then how many spaces? I need 2 spaces here. 1, 2. Okay, right? So now they're aligned. So if you look at the last column, right? 0, the 0 here and the 1 here, they're different. Therefore, the result is 1. In the next one, we have the same. They're different. 1 and 0 are different. So the result is 1, right? Now, when you see this, the fact that you have 0b here, that means that it's prepended with zeros. So essentially, what is in front here is 0, 0, 0, 0, 0b. Because the prepending zeros don't count, right? So you see that 0 and 0, the two zeros here produces 0, and 1 and exclusive or 1 also produces a 0, right? So whenever they're the same, the result is 0. Whenever they're different, the result is 1, right? This comes from Boolean algebra, right? So it's addition modulo 2, right? So 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, and 1 plus 1 is, we'd like to say 1, 0, right, which is 2, but if we have space only for one digit, we keep only the last digit, right? So we're ignoring this 1, and we're only keeping the 0, right? We're doing a modulo 2 addition. We're only keeping, right, one digit, one binary digit, right? So the result is then 0. Again, very useful operator, and we're going to find an application for it. So this is pretty much what we can do with the arithmetic. All right, that's the kind of arithmetic. And then the next thing that we need to talk about is Boolean values, right? We have two Boolean values, which are true and false. So you see that they evaluate themselves. Okay. So what do we do with them? Well, how we produce these kind of values? We use comparison operators, right? So you've seen equal equal before. Equal equal is a comparison, arithmetic comparison operator. It checks whether two values are equal or not, right? So 1 equal equal 1 will yield true. 1 equal equal 0 will yield false. In general, this is a very simple way of evaluating, but if we assign x to the value of 1, let's say, and y, we give it the value 2, right? And this is something that happens in a big program, right? At some point, we might not be very sure about the values of x and y, so we can say x equals y, right? We use equal equal as opposed to the simple equal because equal is used for assignment, right? So we don't want the confusion. The negation of this is x not equal y, right? So whenever equal equal is false, not equal should be true. Okay. Then we have all the other comparison operators that we know of, right? So less than, greater than, right? Less than or equal, greater than or equal. Okay. And then we can combine operators. So I'm going to say that z is 100, right? And we can say x equals y, or, and notice that this is different from the bar. The bar represents the bitwise or, whereas the word or represents the Boolean or, right? True and false are Boolean values. So x equal y, or y less than z, right? So this evaluates to true, right? So x equal y is false, we know that from here, right? X equal y has evaluated false already, right? So this is false. But y less than z is true because z is 100. So when is an OR true? When either the left side is true or the right side is true, right? We don't need both of them to be true. All right, by the way, for OR, we also use the word disjunction. You're going to hear me using it very frequently, right? I'm going to say that this is a disjunction, all right? And we have two sides of the disjunction, the left operand and the right operand. Similar to AND, we have to OR, we have the AND, which is a conjunction, right? And the conjunction requires both sides to be true. It is not the case right now, and the entire expression evaluates to false. Okay? AND binds tighter than OR. So if I say something like true, let's say true and false, the mouse pad is very sensitive and always just a little touch will just move the cursor. True and false, or false, or true and true, right? So you're going to wonder, how does this get evaluated? Well, you know already that for arithmetic operations we have precedence, right? The star, the multiplication, binds tighter than addition, right, than the plus. Here, the conjunction binds tighter than the disjunction, right? So the above expression is equivalent to this one where we have added brackets, okay? So we get the same result. If you want a different order of evaluation, you can use brackets, as you would use in algebra, right? So we can, for instance, do it this way, and we have a different expression this time, right? The result happens to be the same. Is this clear? Okay. We also have the negation operator. If you remember your Boolean logic, you must have studied some Boolean logic at some point, right? You know what true and false and conjunction, disjunction are. We also have the not operator. The not operator binds the tightest of all the Boolean operators. So we can just write not. Going back to our previous example, right? Instead of writing x not equal y, we can always say not x equals y, right? And notice that equal binds more tightly than not, and binds more tightly than all the Boolean operators. It's the same as writing it like this. Now, many languages have different rules for the precedence of the operators, right? C is one of the most is notorious for being very difficult, right? There are many operators apart from the arithmetic ones. There are also pointer operators, and they are difficult. So don't be afraid to use brackets. I will not expect that you should always remember the precedence and minimize the number of brackets, right? Use brackets freely just to make sure that the order of the evaluation is the one that you want. Okay? So we've seen primitive values, right? Numbers, which come in two flavors, right? Integers and what we call them is floating point numbers. And maybe at some point I'm going to get to explain why that is. And strings and Boolean values, right? So there are four of them, primitive values. And what can we do with these, right? We can write a little bit of code. So normally now what I would do is, or what a typical course would do is introduce the while statement, the if statement, and so on, right? I'm gonna diverge from that, and I'm gonna go directly into functions and procedures, and we're gonna try to stay as mathematical as possible. We're gonna try to stay within the realm of mathematics, because you know what functions are from mathematics, right? So that should feel familiar. Yes? Okay, and we're going to explore this relationship. Let me introduce one more operator. All right, so I'm going to say that if x is equal to y, I would like an expression to evaluate to say true, not true, to say 1. Otherwise, I want to evaluate it to 2. All right, so this is a very interesting kind of expression. So I'm going to say that this expression of mine is 2 if x equals y, and actually I don't need the brackets. Let's not add unnecessary brackets. Else 3, and this evaluates to 3. This is an expression that has value. As I was telling you before, pretty much everything in Python has value. So I can take this and say plus 100 here, and let's format it nicely, and I will get 103. Now notice that the brackets are necessary, right? So when I write it this way, this entire thing is evaluated first. Remember that x and y are not equal, right? So the result should be 3. And then we add this to 100. Okay? If I remove the brackets, then the plus binds more tightly than the else. And strangely, we get the same result. But it's because actually this gets evaluated first. All right? So just to make a point, I'm going to say that this is not equal to y, right? And we're going to get the result of 2. And if I go in the previous expression, I'm going to make it not equal, and we're going to get 102, right? So, but this is a very interesting kind of expression, right? Yes? Okay. So, let's learn how to define functions. Okay. The definition of a function is done with the keyword def. So we're defining a function. Let's call this function f, and maybe this function has 2 arguments, right? So then we we write the colon saying that what follows is the definition. All right, and I'm going to use the keyword return, which later is we're gonna learn more about it, but for the time being, all the functions will start with return, and we can return x plus y, or let's return something more complicated, x times x plus y times y. All right, so you're going to have to press enter twice. All right, and we have defined function f, and f now can be invoked. So we can invoke it with, let's say, the values 3 and 4, and we're going to get 25. Right? So it's a function. Now, interestingly, can we define the function that computes Fibonacci? How is Fibonacci defined? Or forget about Fibonacci. Factorial. How is factorial defined? No?
n times n minus 1 factorial.
So, n times n minus 1 factorial. When? Right? And right? So notice that we're using the definition of factorial inside itself. We're using what? Recursion. Yes, very good. This is a recursive definition, right? And there's a question, right? Isn't there a chicken and egg problem? And the answer is no, there isn't, because if I want to compute, let's say, 3 factorial, by this definition, 3 is greater than 0, so it's going to be 3 times 2 factorial, right? Which, by this definition, is going to be 3 times 2 times 1 factorial, right? Which, by this definition, is going to be 3 times 2 times 1 times 0 factorial, and then it's going to be equal to 3 times 2 times 1 times 1, and at this point I can compute the entire value of the expression, right? Yes? So the fact that we have recursiveness, right, it doesn't really lead to a chicken and egg problem, right? And when I say chicken and egg problem, everybody knows what I'm talking about, right? The philosophical question is what came first, the chicken or the egg? Right? And before understanding evolution, right, somewhere in the 16th, 17th century, philosophers thought that this was a very tough problem to answer, right? There would be arguments one way or the other. All right, so factorial, def, factorial n, and then we're going to return something, right? What are we going to return? One if n equals 0, else n times factorial n minus 1. Yes? So now I can invoke it. And there's an interesting thing. Have you ever tried to compute factorial of a value higher than 13 or any other kind of language? No. It overflows, all right? So this is something you cannot do. You can do in very few other languages. Another language where you can do this is Haskell. All right? So typically, the largest number that a programming language can handle is, do you know? Two to the power of when they say 64 bits, what do you think they mean?
2 to the power of 64.
So close enough. It's actually to the power of 63. It's actually to the power of 63 minus 1. But I'm not going to go into details, right? So what happens is that 64 bits means that the processor can handle 64 bits at any one time, right? Which means that there's 2 to the power of 64 distinct values that you can have for an integer. right? Thing is, half of them have to be for negative numbers. So to the power of 63 are minus 1 are, actually to the power of 63 are negative. There's 0, and to the power of 63 minus 1 are positive, right? That's the convention of the representation, right? So close enough. You can think of to the power 64. It wouldn't be very wrong, right? So this is the largest number. And in most programming languages, this is about factorial of 22, right? So between factorial 22 and factorial 23, you're going to get a wrong result. Interestingly enough, the computer doesn't tell you that the result is wrong, right? What happens is that everything is computed modulo to the power of 64, right? So you compute a number, you keep the last 64 bits, right? So you're going to get the wrong result, but you won't know that you get the wrong result, right? So Python is very nice in the sense that it has infinite precision arithmetic. So you can compute arbitrarily large values, and you can actually go, so you've already seen 100, you can actually maximum recursion depth exceeded in comparison. Yeah, I'm afraid you can't do one. Can I do 999? No. Can I do 995? What is the maximum number? $990. Okay, 990. So actually, there's a setting. Recursion depth. You see it here. So we're going to find out how to change that. All right, and this is dangerous, and you should never do it in production. We're going to see how we can circumvent that. We're going to talk about import next time. And now, if I want to go to 1000, there you go, I can go to 1000, right? So this is a huge number. Very few other programming languages can handle this, right? But most importantly, is this definition clear? Does everybody understand this definition? Has everybody run this program right now? Yes? Is everybody clear with this? Okay, we have time to do Fibonacci, so let's do Fibonacci. All right, so what is the definition of Fibonacci? Of n is equal to. So this goes like this: 0, 1, 2, sorry, 0, 1, 1, 1, 1, 2, 3, 5, 8, 13, 21, and so on, right? So each number is the sum of the previous two, right? Where do these numbers come from? Do you know?
Fractal.
Louder.
Fractal.
Just a very Fibonacci in the 11th. Yes, louder. Yes. Why did anybody come with this idea at any point? Why did Fibonacci in the 11th century thought this was an interesting problem to solve? You have a pair of bunnies, right? And let's suppose that it takes 1 month for them to procreate, right, to multiply. So they create another pair, right, of bunnies. And then incest not being a problem between bunnies, right, it takes another month for the bunnies to mature and be capable of procreation, right? So, and then, right, you have 2 pairs of bunnies that can multiply and move on, right? So the question is, how many bunnies do you have after n months, right? So that was the problem, and it's very clear that, right, if you have this many bunnies at some point, right, actually only this many bunnies are mature and can multiply, right? Because these bunnies, we assume that bunnies don't die, right? So these bunnies are included in these ones, right? So in the next month, since only these can multiply, right, you're going to have this number and this number in the next month, right? And then the bunnies that were here but were not here, so 2 minus 1 bunnies, those become adults, right? So then in this month, you have only this many bunnies that can multiply, and that's where the problem came from, right? That's where the series came from, right? In counting how many bunnies you're going to have after X months, right? And it's a problem that is not, it's very common, right? I mean, it's a bit artificial thinking of it, because, you know, bunnies die and then they don't reproduce with very constant frequency, right? So there's a problem. But then if you look, for instance, at the pattern of the sunflower, when the seeds of the sunflower. So if you know the sunflower has a disc, and then there's a little disc here, and then there's a seed, right? So the seeds come in a pattern that is also, follows the Fibonacci numbers, and that's a pattern that comes in nature very frequently. And why? It's because this law of reproduction actually works in a lot of places, right? So the Fibonacci series actually has a lot of significance. This number, which, right, we're going to define it soon, actually has a formula to it, and the formula is not very difficult to prove. Do you know what it is? It's 1 plus square root of 5 divided by 2 to the power of n minus 1 minus square root of 5 divided by 2 to the power of n. Right? So this is actually a number, and it's strangely, right, because these are irrational numbers, but their subtraction is a rational number, right? But we don't want to compute this, right? We want to compute Fibonacci by its original formula. So let's try to do that, right? So fib n is equal to n if n is less than or equal to 1, and fib n minus 1 plus fib n minus 2 otherwise. Yes? Everybody agrees with that? So how does this translate into code? So we're going to return something. For the time being, we just use the word return as it is, right? We have to return something from the function. This is the return value, right? So we're going to return n if n is less than or equal to 1, else fib n minus 1 plus fib n minus 2. Okay, so this is it. Okay, so fib of 0 is 0. Fib of 1 is 1. Fib of 2 is 1. Fib of 3 is 2. Fib of 5 is 5, 10, 55, right, 100. So now trouble is, the way we have defined Fibonacci is it has exponential complexity. All right, so it's it will take very long, right? And we're going to learn next time how to make it faster. So I think even 20 is going to take too long. Oh no, 20. Okay, but you know, this is how we can define Fibonacci. All right, so we want to take advantage of math as much as possible, right? These definitions are recursive. All right, there are certain disadvantages to recursion, and we're going to talk a little bit about them. What I would like you to do is dig into your math knowledge and we're going to try to find computations taking advantage of recursion, right? Because it's purely mathematical, and hopefully it will help you design algorithms and find, you know, write code. Will make it easier for you to write code in the beginning. Cool? Yeah. Okay. Questions? No? All fine? Cool. Thanks for coming. See you next time.